Okay, so what we'll do is we were looking at logic families, and there was one particular discussion which was sort of incomplete, which was related to dynamic logic. All right, so let's continue with that. So just to remind you, we were looking at different ways of implementing basic gates, and we said that we should evaluate those basic gates, basic techniques for implementing gates along these particular dimensions here: simplicity, delay, power, noise immunity, and how it scales with number of inputs here. And so this is the default family that we have, the fully complementary CMOS. And with that, we had seen it has many advantages, widely used. The trouble with this is the fact that we use 2n number of transistors. For a 2-input gate, you need to use 4 transistors, or for a 3-input, you need to use 6 transistors here. And so that's the problem. The other one is you get a long chain here, whether it's a NOR or a NAND, either a long chain of NMOS or a long chain of PMOS. That causes problems in terms of drive capability. So as an alternative to this fully complementary CMOS, the one alternative was that if we replace all the PMOS part here with a single PMOS transistor here. So instead of building for every input a PMOS transistor, if we just have a one PMOS pull-up load, and the NMOS are over here. And so if we can build a logic like this, so we can build a very large number of input NOR gates. For example, for this is 2-input NOR gate. For a 3-input, we need to add one more transistor. For 4-input, another, and so on and so forth. So large NOR gates become easy to realize. And using NOR gates, then of course you can realize OR and 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 other things as well. Right, so that was the advantage of this particular logic, where you replace the entire PMOS by one single PMOS load here. But the disadvantage was that this one had static power dissipation. And it was a ratioed logic. Ratioed logic in the sense that the output, once it is low, the low value depends on the ratios of these transistors here. So that was the problem. And so the issue was that, can we sort of preserve some of the advantages of this particular logic and eliminate the disadvantages that are there here? So with that motivation, we had looked at one particular alternative. So today, let's look at the other one here. So we start with this, and the idea is that to eliminate the static power dissipation and to eliminate the fact that it's a ratioed logic, consider the following alternative here. So this is a clock-driven logic family. So every gate is clock-driven here, and this is the clock here, phi. And so and this is the normal pull-down network. Whatever is the pull-down network here, the same pull-down network over is here. And this is the pull-up, which is same as here, except that it's not always ground. It's driven by a clock here. And another pull-down transistor has been added here. And you'll see why these are there. First of all, note that compared to a fully complementary CMOS, this is going to have, if this has n number of transistors, a fully complementary CMOS would have had 2n, and in this case we have n plus 2 transistors. So obviously, if we look at number of transistors, it's simple. All right, how does it work? As we had looked at earlier, the operation of this is based on 2 phases. The first part is what we call as the pre-charge phase, where every node that you see here, so clock, this phi goes low, so phi is 0 here, and obviously if phi is 0 here, note that the pull-down network, this transistor is off, and it doesn't matter what this particular transistor is. So the pull-down network sort of disappears, and phi is 0 here, PMOS is on, and it charges the output to VDD. So that's the first part. The output node is charged to VDD here. The next, so this is the pre-charge phase. It's sort of preparing this particular node. Now, 2 things will happen for the given inputs. Either this node will be low or high. Now, if for this inputs, the node is supposed to be high, then it's already in the right state. On the other hand, if for the given inputs, the node is supposed to be low, Then you go to the evaluate phase here, evaluation phase, where the clock goes 1, and so this part disappears. It no longer works here, and this is 1 here, so the transistor is enabled. And the transistor is enabled, so now depending on the input here, if the input is low, then you get VDD. Nothing really happens, it's already at VDD. On the other hand, if input is 1, then the output goes to 0 here. All right, so that's how you get the right output when the clock goes high here. So it works on this particular principle here. Now, if you go back and look at it, see, if you go back and look at this particular logic here, these two, the disadvantage was that when the output goes low here, there was a direct path from VDD to ground, and that was causing static dissipation. Now we don't have a direct path. Either note that when this transistor is on, so we have a path here, this is on, then this transistor is off, right? So there's no direct path from VDD to ground here. So there's no static power dissipation. And the ratioed logic was also coming because note that when you turn the pull-down network on, this is also on. So you have so this transistor is trying to push this node to VDD, while this pull-down network is trying to push it to 0 here. And we want it to be 0. So we have to adjust the sizes of this pull-down network compared to this so that this is indeed pulled down to a relatively low value here. So that's why it was becoming ratioed. Why? Because both of them are turning on. Now we note that either this is on, the pull up here, which is simple, or the pull down is down here. So it's no longer a ratioed logic. It's a ratio-less. So you can choose any size here and any size here. The output value would be the right value of 0 instead of some non-zero value here. So both these disadvantages of this particular logic you can see here are overcome in this particular one. No static power dissipation, and it's a ratio-less logic here. But then these things, that advantages that you see here, they are coming at a price. So let's understand that. So this is the evaluation phase. And as I said, instead of a single NMOS, you can put whatever logic that you want. If you put 2 of the NMOSs in series, it becomes a NAND gate. If you put 2 of them in parallel, it becomes a NOR gate. So you can build, this is a general purpose logic you can build, all right? All right, so this is the way this works here. The problem is the floating node. There's a possibility of a floating node at this particular point. Consider this in the evaluation phase. When I'm evaluating, so my clock is high, both of them are high here. And suppose the input is, so this is high, suppose the input is 0. So the input is 0, the node is pre-charged to VDD, and the pull-down network is deactivated, and this node is supposed to hold its value to VDD. But then this is what I was trying to point out here. This is supposed to hold it to VDD. But then this is what I was trying to point out to you here, is that when this is a situation, look at that in evaluation phase. So upper part doesn't matter. This is ground. And lower part, this is VDD here. So this is enabled, clock is 1. So this is the situation. And I want this output node, which is floating, to remain at VDD. But then this transistor that you see here, it has a leakage current. So this capacitor here sort of leaks charge. Not only that, note that as if this voltage, if there's a noise on this particular ground line, and our threshold voltage is 1 volt. So if the noise here rises to 0.4 or 0.5 or 0.6, the leakage here increases significantly. And then the capacitor begins to discharge. So you want it to remain high as logic 1, but the charge leakage may cause it to deviate from a normal one. It may even go to an incorrect logic value here. So that's the problem with this particular logic here, in the sense that you have a floating node, and floating in the sense that is neither connected through a transistor to VDD, nor is it connected to ground, right? So it's just floating. And any other source of noise, for example, I'm just pointing out a noise in the ground here. If the noise voltage in the ground, if it rises for some reason, then this particular capacitor will discharge. And so that's the problem with this one. Vin greater than 0 causes charge to leak away. And the VIL, note that this input that we put it to ground, how high can it rise? Well, if I reach VIL equal to VTHN, there's a lot of current flowing through the transistor here. And obviously you'll get a wrong device here. So VIL, the maximum input that I can apply at this particular gate, and still the logic works properly, will be significantly less than threshold voltage. So if it is 1 volt here, perhaps I can apply 0.8 or 0.7 or 0.6 at this particular value and still hope that this particular logic works properly here. In contrast, remember that fully complementary CMOS, we were getting VIL close to 1.4, 1.45 or so. So we were getting a much better noise margin. So noise margin is going down because of this particular phenomena here. The other one is note that it's a non-restoring logic. What do I mean by that? Non-restoring in the sense, look at this normal fully complementary CMOS gate. Normal fully complementary CMOS gate, you apply a 0, you get a 1, obviously. Now, suppose for some reason we had seen earlier in earlier lectures that there is a glitch here. That is normally 0, and it momentarily goes to 1 and then comes back to 0 here, momentarily, okay? And so we were calling this as a static 0 hazard and static 1 hazard and all that. So suppose this happens, there's a glitch here. Well, the glitch it may temporarily cause a problem here, but it doesn't cause any permanent change to the output here. Okay, so for example, I've just shown you a simulation result. Note that this is the input, the blue is the input here. So there's for a short period of time, there is a glitch at the input here. The output, which is supposed to be 1, which is here, sudden glitch you apply here, the output goes and falls here, right? Because you've created a 1 here, so the output tends to start to discharge. It starts to go to 0. But the glitch is very short, so it doesn't completely discharge to 0 here. It discharges here. But note that the moment the glitch disappears, that the output returns to 0, it again charges back to the normal value. So that's why we call it as a restoring logic. If there's an error, well, the output may start to show some deviation, but the moment the error goes away, the output returns back to its normal state. It's a restoring logic, okay? Because there's the moment it goes to 0 here, this transistor is on, it will pull it back up to 1. Now, look at this particular logic here. So this particular logic again, so what happens is this is off, and there's a glitch here on this side. If there's a glitch here, look at what happens here. Glitch here, so this is supposed to be 0, and there's a glitch, it momentarily goes to 1, the transistor turns on, and this particular node discharges. And then the glitch disappears, but then this has already lost its charge. It's a floating node, and it remains at this particular point here. It doesn't go back. It's non-restoring. That's the problem with the floating node. How to be? It's continuously coming. Its continuous clock is there. 0, 1, 0, 1, 0, 1. When 5 changes next time, then when 5? Yeah, when 5 goes back to 0, then it will go back to its normal state. It will pre-charge to 1. But during that evaluation phase, if for some reason when this is 0, this is 1, if for some reason the input shows a glitch, if it comes, then this particular node will discharge and will stay there till the next clock edge comes, right? So it doesn't restore back, it doesn't go back here. And so that's another problem. It's a non-restoring logic. A glitch can potentially cause a permanent error. Permanent error in the sense for the entire evaluation phase, it will remain now at this lower value here, okay? So that's another problem. That's all because of the floating node here. The other problem is, the way logic exists right now, cascading is a problem. A single gate by itself is of no use. You have to connect one gate to the next and see that it works properly. And so if you look at what we have done is we have taken 2 NAND gates. One NAND gate connected to the other NAND gate here. So let's look at the operation here. AB is here and C is here. So let's look at the operation. Suppose A and B are supposed to be 1 and C is 1 here. So the normal output that you expect here to be 0. And if this is 0, then you expect a output 1 here. So that's the normal output. Okay, so now how does it work? So how does it work? Now, note that so initially what would happen is when phi is 0, this node will pre-charge. Okay, will pre-charge, and so initially it is 1. And then when you go to phi equal to 1, so this node has to discharge, right? Because its normal value is supposed to be 0. So initially it is 1. Note that initially it is 1, and then it goes to 0. It will take some time to go to 0. But note that during that interval, this node is 1, and this node is also 1 during the evaluation phase. Both of them are 1, and what will it do to this particular node? This node is floating, Supposed to be floating is supposed to be 1 here because it's disconnected from here. And this is still 1, it's not gone to 0 here. It may not be 3.3, it may be 3 or 2.9 or whatever it is. It will take some time to discharge. So during that period, there is a path to the ground. And so this particular node may sort of discharge. And then you may not get a proper 1 here. Okay, so that's a y. So the point is that the correct value of y is 0. The correct value of y is 0. But remember, initially it is charged to 1. And then it will drop to 0. When it reaches these particular values here, it will drop to 0. But it takes time to drop to 0 here. And during that time, the input to this particular gate is incorrect. The input is incorrect because it's supposed to be 0. But it's still making a transition from 1 to 0 here. So the input is incorrect, and therefore it may cause a error at this particular one. So cascading is an issue here, as you can see in this particular case here. So I took this one, and the blue is the clock part here. The blue is the clock part here, and Y shows the this thing. Y shows the output here, and Z1 is in the green one. So note that when you go to the evaluation phase, when the clock is high, then Y, which was 1 here, Y here, this red one starts to discharge. But note that for a certain period, Y is still, it's not 0. It's supposed to be 0, but it's not 0. And so this Y is going into the next gate, and look, it causes a little bit of discharge of the output here. In this case, it didn't cause too much, but note that if I cause some loading of this particular gate here, another simulation where Y takes more time to go to 0 here. Y takes more time to go to 0 here, and note what happens to the Z here. Z discharges even more. All right, Z discharges even more here. So this is sort of problematic. Now, in the sense that I want here to be VDD, and this particular node is dropping because the input is momentarily incorrect here. The input is not gone to 0, it takes some time here. So cascading in this particular manner can potentially lead to errors, and this cannot be tolerated. So this particular gate, I can't take this particular gate and simply cascade to the next particular gate here. And so what we need to do is add a inverter to it. So note that we have this normal gate here, phi here, this is AB. And what we do is we add an inverter here. Now, how does an inverter solve a problem? Look at this one. Why is it causing an error? Because this node was charged to 1, and then the correct value is 0, right? But note that 1, when you have a high and it goes to a NMOS transistor, a high input for an NMOS transistor is an enabling input. It turns it on. It turns it on. Right? So, and that's why then depending on the value of C and all that, it causes a problem. But suppose I add an inverter here to this particular gate. So I still pre-charge it to 1 here, but the output here is 0. Now note that if I add the other gate, now you'll see that there will be no problem. Because, okay, if it pre-charges to 1, so let's say this is 1, 1, 1 here, and we apply a 0. We apply 0 here, clock is 0. So this particular node charges to 1, and this goes to 0. Okay? Now the correct value is not 1. The correct value is 0 here, and the correct value is 1 here. So it may take time, but note that because it's 0, when you apply a 1 and 1 here, fine, it will take some time to drop to 0. It will take some time to go to 0 to 1, but it's not causing any error in this. Why? Because 0 is a non-enabling input to the NMOS transistor here. It's not causing any error here. Because normal, you see, so what you're doing is the output is sort of you're pre-charging it to 0. Now the 0 value may be incorrect, let's say. But then an incorrect value that goes to an NMOS doesn't do anything to the NMOS. Right? NMOS doesn't turn on and doesn't cause an error here. And when this value here is 0, it goes to 1, then the NMOS turns on, and then the appropriate value of the output reaches, and then the output, the final output is also correct here. So this, one is able to cascade this dynamic gate to the next gate here only if we add an inverter here. Otherwise, as I just showed you earlier, cascading, normal cascading, if you don't use an inverter, normal cascading causes a problem. It may incorrectly turn on a transistor, cause an output to discharge, and give rise to an incorrect value here. So this dynamic gate that you see here with the inverter like this is what we call as a domino logic. Domino logic here, and so it goes fine properly here. The problem with this one is that it becomes a non-inverting logic. Non-inverting logic, because if you look at this A and B, whatever I put in the pull-down network, A and B, so the output here is AB bar, and AB bar, and then it goes through an inverter, it becomes AB. So you get only a non-inverting logic. You can get an AND gate, you can get an OR gate, but you can't get an inverter. You can't get an AND gate. So it's all non-inverting logic. So that's potentially a problem. At various points in when you're doing your building logic circuits, you need inversion. And this doesn't provide inversion. It only provides non-inverted outputs here. A plus B or A dot B and all that. So that's the problem. So somewhere, what you'll have to do is use some other logic family, a CMOS in regular CMOS. And by the way, note that we have used a regular CMOS inverter here anyway. It's not a pure dynamic logic. So it's a new logic, but a CMOS inverter has been used. And similarly, wherever you require a logic inversion, if you had to get a logic inversion, you'll use a regular CMOS inverter to invert it. Okay, so that's, but potentially now, at least this particular logic now is ratioless, doesn't have static power dissipation. You can cascade one gate to the next. All these things are fine. And the other is simple. Note that if you just compare a NAND gate, it doesn't look simple. A NAND gate, in this case, requires 4 transistors here, 4 plus 2, 6. A regular CMOS gate requires only 4. Right? It's not simple. But think about if you want to build a 10-input OR gate. A 10-input OR gate, one could take these here and put them in parallel. I can take 10 NMOSs and put them in parallel. So I get an OR here, and then I get an OR here. Right? So I get a 10-input OR gate. I can build relatively easily with this one. A 10-input OR gate, you would struggle to build with a regular CMOS. You will have to use multiple gates and becomes more problematic here. While a 10-input or a 15-input OR gate you could potentially build with this particular logic. Floating nodes are still an unresolved problem. We still have a floating node here. We have not solved the problem of floating node. We said, remember all this, if the input rises, if it becomes, both the inputs become close to threshold voltage, the node will start to discharge. So floating nodes are still a problem. We solved the cascading issues here. Now I want to show you floating nodes are not just because this transistor may have some leakage current and cause this particular node to discharge, but floating nodes are also a problem because of a charge redistribution issue. Charge redistribution issue. So look at this particular gate here. Right? So we have A here, we have BDE here, and we have C here. So you can calculate what this particular logic does. And the normal gates are here, transistors are here to which the clock goes, a PMOS and an NMOS here. All right. So this is our domino gate. Now look at, consider the following. Okay, can everybody figure out what this will do? B plus D plus E, they're in parallel. Dot A, dot C, and the whole thing bar, right? But the whole thing bar will appear here, and then there's another bar. So it's basically B plus D plus E, ANDed with A, ANDed with C. So that's what this particular logic does, okay? Now consider the following. We have 0 and 0 here. And note that these inputs that you see here, A, B, C that you see here, where are they coming from? They're also, let's say, coming from previous domino logic gate. So note that during the normal pre-charge phase here, the output of a domino is 0. So if A is coming from a domino gate like this, so A is also initially all 0, 0, 0. Okay? So you apply, the clock is 0, this is 0 here, and note that what happens. if this is 0 here, this particular node charges to VDD. What happens to this node here? Suppose they were all initially discharged. Capacitance C2 doesn't charge. You know, from VDD, this transistor turns on and charges C1. Fine. But the input to A is 0, so this transistor is off. C2 doesn't charge. All these transistors are off, so C3 also does not charge. And C4 also does not charge. All the C2, C3, C4 are all discharged, all 0. Now, let's go to the evaluation phase. So only C1 is pre-charged here. Now you go to the evaluation phase. So it becomes 1, and this is 1. And suppose my inputs are such that this is 1, 1, 0. Okay? For one particular case here. So now this is off. And note that this transistor is on, and this transistor is on, and this is off. So what would happen is the charge on this particular capacitor here will now redistribute, because this transistor is on, will start to charge C2. C1 will charge to C2, and because these D and all these are also on, it will start to charge C3 also. So the charge on C1 is now redistributed over C1, C2, C3. So fine, earlier this particular node was charged to VDD. It had a voltage of VDD. But the charge now is redistributed among C1, C2, C3. So if the charge is redistributed, it means that the voltage falls. So again, it will not be 3.3, the voltage will become some lower value here, right? And so what is being pointed out is that once a node is charged, then because of this charge redistribution problem, the node voltage may not be 3.3, it may be 3, or it may be 2.9. So to begin with, the voltage may be lower here. And then on top of that, you have leakage problems and other things that further contribute to loss of charge here. So this floating node is for various reasons is problematic. A node which is pre-charged to VDD, and then because there's no path to the ground here, so it's left floating at VDD, is problematic. So in order to remove that particular problem, one of the ways is take a domino logic and add what we call as a voltage keeper. So this is our normal domino logic here, and what is added to it is a PMOS. So now note what is happening is when you're giving 1 and 1 here, and in the evaluation phase, and let's say this is 0 and 0. This is 0 and 0. So this is supposed to be floating. And but if this is floating, this is supposed to be 1, and the output is 0. Inverter is connected, and this 0 goes to a PMOS and turns the PMOS on. So this particular node is no longer floating, right? This node is connected through a PMOS to VDD here, right? And this PMOS is deliberately kept as a very small PMOS here, because its role is just to supply enough current here so that this node does not go to, if there's a charge redistribution or something, or if there's a leakage current here, this particular transistor just keeps it to 3.3 here. So that's the purpose of this particular transistor here. So with that, this particular node then is no longer floating, but a weak PMOS is added, which sort of maintains it towards the normal value here. But then there is a bit of an issue here. So this is okay. This node is supposed to be 1, and the PMOS sort of keeps it at 1. But then look at this particular situation here. This is 0. Let's say this is VDD here, and this is high here, and so this is supposed to be 0. This is supposed to be 0, and this is supposed to be 1 here, and it's supposed to. So it's 1 here, so PMOS is off. So that's not a problem. But then that's not the issue. Initially, what was it earlier? It was 1. It was 1. This was 0. And so this is 0 here. And so PMOS is on. Now these transistors are trying to pull it down. But what is the PMOS trying to do? Because of the 0, it's trying to maintain it to high value here. So this is what we call as contention. A node is being contested, in the sense that these transistors are trying to pull it down, while it has not really gone down yet. It is still high, and therefore this is low, and this PMOS is trying to pull it up. So that's not a good thing. Normally, you know, when we turn a particular pull down or a pull up network on, if we turn a pull down network on, we want a pull up network to be off, because the currents and all that then are all available for discharging that particular node. But here, note that for a while there is a contention. For a while there is a contention because this PMOS is also on, and these are also on. These are also on. So that's sort of a problematic part. And for that reason, note that this is kept as very weak. 4 lambda by 2 lambda, and the sizes here are kept large so that the strength of the pull down network is significantly higher than the strength of the pull up. So it's able to pull it down, but still there's a loss. There's a loss of, because there's something else that is trying to maintain it to high value. So this sort of causes some issues here. But this is a viable way of making a gate, a dynamic gate, by adding this inverter, which solves the problem of cascading, and by adding a what we call as a keeper, a voltage keeper transistor, a keeper transistor here, which tries to keep the output here close to VDD here. So a viable way of doing it, and it is is considered as one of the fastest ways of implementing logic. The capacitance at the nodes are not very high. All that you get is a contribution from one single PMOS, as compared to a regular fully complementary CMOS, which gets contributions from a lot more transistors here. And any input that you apply here sees only one gate, one NMOS. While in a fully complementary, an input that you see here will go to a NMOS as well as a PMOS. So the input capacitances are also low. So I don't know the status right now, but in many of the early microprocessors, whichever was the critical path where you required high speed, logic like that would be used. A domino logic kind of a gate would be frequently employed to get higher speeds as compared to fully complementary CMOS here. Another way in which you could solve the problem of cascading is by, before that, so some people also try to, in order to improve the speed of the transistor here, what they try to do is remove the this particular transistor here, the lower transistor here. So that has been removed because, remember, the more the number of transistors that you add, the pull down strength decreases, the longer it takes to pull the node back to 0 here. So this particular transistor is sort of removed to improve these. In many of these high-speed designs, this particular transistor, it goes by the name footer. It's like the foot of the this particular gate here. So it's called a domino without the footer transistor, right? So without this particular one. If you're anticipating that there can be potentially a problem, in the sense that when phi is 0, so this PMOS is on, and what if A and B are also on? What if A and B are also on, and then there is a direct path to the ground, and that cause. So in that, care is taken that when phi is 0, the A and B, remember the normal output is 0. The normal output, pre-charge output is 0 here. So when during the pre-charge phase, care is taken that A and B will not be on. Huh? No, it will not be ratioed, because care is taken that the two are not simultaneously on. A and B, note that A and B are also the result of a gate like this, right? So when phi is 0 here, and when you're pre-charging, the output is supposed to be 0 here. And so the output is supposed to be 0 here. But then you have to take care, because initially it may not be 0, it may be 1, and then it may be dropping to 0 and all that. So very often what happens is the A and B, they may be coming from previous gates, and the clock for that particular gate may be delayed with respect to, or the clock for this one may be delayed with respect to the clock of the previous gate here. So what they do is the different levels of gate, this may be level 1, and there may be another level 2 and level 3. So the clocks for different levels are slightly delayed to make sure that this never happens. When phi is 0 here, the A and B are not high, and you don't get a path to the ground. So by delaying the clocks from when you go from one to the one level to the next level here. All right, so the other one is, there's another solution to the cascading problem. Note that cascading problem was because the output is pre-charged to 1, and if 1 is the incorrect output, then 1 sort of enables this particular gate and causes incorrect output over here. Now, we can solve this particular problem if the output here from a gate like this doesn't go to a gate where to an NMOS, but it goes to the gate of a PMOS. Suppose this is the normal dynamic gate that we talked about, and we don't use an inverter, and the output now doesn't go to another NMOS. Because it was going to an NMOS, pre-charging to 1 was causing a problem. It was turning an NMOS off. Now what we are saying is, okay, it's pre-charged to 1, but then it doesn't go to the gate of an NMOS, it goes to the gate of a PMOS. So now note that if this is 1, and let's say 1 is incorrect. If 1 is incorrect, but it doesn't do anything to the PMOS, PMOS is off. And once it goes to 0, then of course it turns the PMOS on and proper operation takes place. So the idea is that we build one dynamic gate with NMOSes that you see here, and then we follow it up with another gate where it is PMOS. You can see that these are sort of complementary if we also invert this. If we also invert this, then you can see it's complementary to this particular one here. If when this is phi is 0, the output is pre-charged to 1, right? And when phi is 0, what happens to this one? When phi is 0 here, this is off, and phi is 0 here. So this is on, and the output is pre-charged to 0. So it's complementary. This one works on pre-charging to 1, and then during the evaluation phase, either is pulled down or remains up, while this one is pre-charged to 0, and then during the evaluation phase, when phi goes to 0, then it's either pulled up or it remains 0 here, right? So one can cascade one such dynamic gate to the next gate here, provided the output of one goes to the PMOS of the other. And similarly, the output of this cannot go to another PMOS gate. The output of this, because 0 is an enabling input for a PMOS. So the output of this has to go to the N-type here. So you would have a gate like this, followed by a gate like this, then followed by another gate of this type. Okay? And when you do that, what you end up getting is another logic family you can call, which goes by the name NORA Logic, no race logic here. Right? So look at this one. A pull-down network, a pull-up network here. So you can directly cascade. You can take a logic like this, you can directly cascade here to a pull-up network here. But if you want to take this output and you want to give it input to the pull-down network, then you will have to add an inverter to make sure it works fine. All right. And similarly, if you want to take this and add it to a pull-up network here, you'll have to go through an inverter. But you can directly go from here to a pull-down network here. So you can alternate a logic like this with the logic like this here, right? And then build. So this is I'll not go into the details. Why is it called no race and all that? For historical reasons, these are clocked gates. They are all driven by clocks, and the clocked gates had some problem of proper synchronization and race problem issues and all that here. So this is another alternative way of building logic here, with a N-type here followed by a P-type here. But P-type, of course, is more costly, takes up more area. So those are the issues with the P-type logic over here.
In the last previous
so
when the Y goes from 1 to 0, then also for some part, like when it reaches near 0, then also that PMOS will turn active.
No, so 0 is the right output, right? 0 is the right output. So it doesn't matter. 0 is the right output. So note that the problem is that when you pre-charge, you have an incorrect output. So the incorrect part, which is 1, doesn't do anything to the PMOS. It doesn't turn the PMOS on. So remember, if 1 was the correct output, it would have remained at 1 and no problem. But the correct value is 0. So it takes time to go to 0, but then it doesn't do anything. When it goes to 0, PMOS is supposed to be on anyway. It should turn it on. And after a delay, it turns it on. So there's no error. The error occurs only when the incorrect logic, when you pre-charge, so it's sort of, it's pre-charging a node to VDD. But I don't know whether it's VDD or ground, the right value. If it is wrong, VDD is wrong, then the wrong value should not propagate. It should not turn a transistor on and cause an error here. So in this case, when you turn it on high, a high value doesn't do anything to the PMOS, remains off. So no error or anything occurs at this particular point. Okay. All right. So what we have done is, last lecture we were looking at, this was one part of the course, which we call as the front-end design, where given the specs and all that, and you design, do an RTL, and you do the data path and controller and all that. And this is what we've, in the later part of the course, this is what we have, in more recent lectures, this is what we have been doing, looking at how we can implement all these different elements, all these different blocks that you see using elementary gates. And in the process, let me just summarize, this is our main, this is the main bread and butter that people say of CMOS, a fully complementary CMOS. Whatever that you see here is complemented in this particular part, is the dominant logic here. But we have seen that it has problems. Now you should be able to recognize that this is a pseudo NMOS logic. What are the problems that this logic solves? And what are the disadvantages that it has, right? And in an attempt to overcome some of the disadvantages, we end up getting this particular gate here, right? This was the differential cascade switch logic here. Solves some of the problems that you see here. This is one way of addressing some of the problems of this particular logic. The other way that we saw was this one here, by building a dynamic gate, right? It solves some of those issues. And, this evolves into a NORA logic that you see here. The other, which is sort of totally different from all of these, was this Pass-Transistor logic, right? So these are the broad classes of broad ways in which you can implement a logic. Now, there are more things. What people try to do is they try to mix these things in the sense that you don't have a fully complementary CMOS and you don't have a pass transistor. They try to mix both of them. They'll have a pass transistor somewhere inserted and they'll have a fully complementary kind of a thing. So it's sort of a mixture. All right. So these are like, in some sense, these are pure forms of fully complementary, pure form of full, pseudo NMOS, pure domino logic, and pure pass transistor, complementary pass transistor logic. But you can mix elements of these and construct something which is more efficient here.